So here's a pendulum, just like spring. So you pull the spring to some distance and then let go of that spring. It will oscillate up and down. So same thing with the pendulum. You move it either to the right or left at some angle, and then you let go of that. So it will swing back and forth like that. So this is also a simple harmonic motion. So let's slow it down. So see, when it's moving this way, something is pulling this mass to the right. That's why it returns back. And when it's moving to the right, something is pulling towards the left. That moves it back to the left. So there is a restoring force that is causing this kind of back and forth motion. If there were no restoring force, it would just move that way forever. But because of the restoring force, it goes to the right and then it comes back. And again, now there is another restoring force, which is this way. So it's due to that, it comes back. So we want to know what that restoring force is in this case. So to answer that, so that's the simple pendulum. So when it's at this point, so let's say this is the angle. So what forces are acting on this? There is tension. There is gravity. Now, we are trying to find the restoring force. So when it's moving this way, there is restoring force in opposite direction. So we want to find this restoring force. What's that restoring force? So it's not tension, because tension is pointing that way. So that's not the restoring force. Not the restoring force. Okay, our purpose here is to find restoring force. So let's break this weight into two components. So we have this component of the weight and this component. So it seems like this component is the restoring force. Okay, so that's because it's pointing opposite to the motion. This is moving that way, and the restoring force is opposite to that. So that's restoring force. So we want to find that. Okay, so this angle is theta, so that would also be theta. So then the component that is close to this theta would be cosine, and this component would be W sine. Okay, so restoring force in this case, F restoring force equals W sine theta. And we also need minus sign. This minus sign means restoring force and the displacement, angular displacement. This angle is displaced in this direction, and restoring force is in this direction. So they are always opposite to each other. So now we can write this as F restoring force equals W is mg sine theta. Now there is a rule in trigonometry which is called small angle approximation. This is a very useful approximation. You will be using this in physics 2 also, if you plan to take physics 2. So small angle approximation is if this angle is small means less than 5 degrees. If theta is less than 5 degrees, then you can replace sine theta by just theta. So let's use small angle approximation here. So using that, we can get F restoring equals minus mg theta. This is theta. That's the length of the pendulum. And this arc length, we can write that x. So what's the relationship between this x, L, and theta? So in trigonometry, you have this x and this is r. So S is equal to r theta. So we can write, in this context, we can write x equals L theta. Okay, from trig. So we can write F restoring equals minus mg theta. So theta would be x over L. So F restoring is minus mgl times x. So if I have a spring, what's the restoring force? So this is for pendulum. For a spring, mass. What's the restoring force? Negative kx, right? So negative kx. So if I compare these two restoring force term by term, so we have restoring force for pendulum, restoring force for spring mass, displacement for pendulum, displacement for spring mass, and this thing must be like spring constant for pendulum and spring constant for spring mass. Okay, so these two are equivalent. K is mgl. This one is for pendulum and this one is for spring mass. Okay. Again, we are comparing these things term by term, f, x, x. That means this thing must be, we have also negative sign, so negative, negative. So that must be equal to k. That's what I have here. That means if the time period for spring mass is given by 2 pi square root of m over k. Now, if this is the time period of spring mass system, then the time period of pendulum would be 2 pi mass of pendulum, and this k would be replaced by that. Okay, because for pendulum, this spring constant is mg over L. Mg over L. Okay, so let's replace that by that. So time period for pendulum is 2 pi, cancel mass and mass, so L over G. Now what you can see from this formula is time period. So see, there is no mass in this formula. Unlike in spring mass, we have mass, so spring mass time period depends on mass. But this time constant or time period doesn't depend on mass. So T does not depend on mass for pendulum. Okay, this is not for spring mass. I'm talking about pendulum. Also, it does not depend on the amplitude, how far you move the mass. So let me show you that. So it doesn't depend on mass, how heavy this is, it will have the same period. So whether it's that much mass or that much mass or that much mass, the period is not affected by how big the mass is. Also, this amplitude does not affect the time period, whether it starts from here or starts from here, starts from here, the time period is always same. Okay.